All right. Then what? So, so that by the bounded convergence theorem, not to be confused, of course, with the thing we're proving, which is the dominated convergence theorem, right? The bounded convergence theorem. Have the integral over En of f little n minus f man, I guess he does mean to have a little n here. I just don't know what the little n is. I guess the little n is it an n beyond big N or something? I mean, a little hazy on that part. Epsilon for, as he says, all large n, little n. I mean, fine, the big N, right? I guess that's the thing, is for a given epsilon, you can fix a big N such that the integral over the complement of E big N of G is less than epsilon. And then once you know that, you can take that fixed big N for that fixed epsilon and multiply it by F sub N, where F sub N is what? It's one of your sequence of measurable functions, right? I mean, the supporting, so to speak, the zeroing of this function outside of a certain set, it's all happening from this chi En, you know? Chi En is the thing that makes this supported on a set of finite measure. It doesn't really have anything specifically to do with F sub N. So I don't think it's a typo, actually. I think that this is intentionally not the same N. Yeah. Okay, so now, and then the end game here. Don't tell me about it, otherwise I kill you. Integral. Let's see here. I've got 5 free tickets. I'm working on my 6th. Let's see here, En. Fn minus f plus the integral. Ooh, very sneaky. En complement. Right? Because that's everything. Uh-oh. A banquet? A banquet? You'd rather go to a banquet than hear about Fourier transforms? How dare you? How dare you? What? We can talk about the complex function part. That probably would be important to do to make sense of the Fourier transform. I better do that. Yeah. Well, I would say have fun at your banquet, but that seems like, I don't know, personally, it's not likely. There's food lots of places that aren't a banquet setting. There's math club. You're skipping math club to go to a banquet? You monster.
I have the basketball deck. Do you care if I just email it to you?
Oh, that's fine if you want to do that. I'll take it like that.
I have to do like the very last part of one problem. So.
Take your time when you're ready. It's fine.
All
So,
right.
Banquet. Banquet. We don't need no stinking banquet. All right. What's that? They charge $10 too? Oh, come on. That's a ripoff.
I send out email 3 times, 4 times, and I just ignore it. Like, it's not worth it.
All right, so do we understand why I'm writing what I'm writing at this point here? He replaces he replaces Fn minus F with G. How does he get from Oh, it's this? All right, so I'm the only one here who can't see this inequality. I'm not saying, yeah? Oh, that's why there's a 2 there. I'm an idiot. Oh, okay, I got you. So you're like, this is just... Or, well... And so that's integral of G, and that's also integral of G, right? Which you're like, yes, but of course this is just equal. Come on, so much writing. And then we just work to show that that was less than epsilon. This is less than, so we got, what, epsilon plus 2 epsilon. Which of course is 3 epsilon. Great. And what does that show? For n large enough, we can make the integral of the value of fn minus f as small as we like, which is to show that this goes to 0 as n goes to infinity, right? So thus this integral goes to 0 as n goes to infinity, and then of course that directly implies this. Yay! All right. Bounded monotonic sequence theorem. Now, next up, he defines integral of complex valued functions. That should take us considerably less time. So we've been doing real valued functions of a variable in Rd for most of this integration theory. So here's how complex valued functions goes. This will be important as we try to talk a little bit about Fourier stuff in the time that remains. Maybe not today, but maybe next time. I don't know. We'll see. So he says, if you have a function that's going from Rd to the complexes, you can write f equals to u plus iv, where u is like a so, and v is like a so. Now, we've already described the integration theory for u and v, because these are real valued functions of a Rd variable, right? And so what he says is that f is measurable if and only if, guess what? Both u and v are measurable. We've already defined what that means previously, right? If the real and imaginary parts of a complex valued function are measurable, then it's measurable. And f is Lebesgue integrable if the absolute value of f of x, or really the modulus, anyway, it's this, the square root of u of x squared plus v of x squared is Lebesgue integrable. And that's a notice that the square root of ux squared plus vx squared is a non-negative real valued function. So we have previously defined what it means to be Lebesgue integral in that sense. He points out fun facts. Fun facts. The absolute value of u of x is less than or equal to the extended absolute value of f of x, or the modulus of f of x, if you like. The length of f of x as a complex valued function, anyway. Let me just say absolute value of f of x. It's just lazier and easier. So the absolute value of v of x is less than or equal to the absolute value of f of x. What that's really saying is that the real part of a complex vector is at its longest the length of the complex, right, number. The imaginary part of a complex number is at its longest the length of the complex number. You can't have a complex number which is shorter than both of its real and imaginary parts, right? Unless you're working with a non-standard, yeah. This would not be typical, but if you had a basis like this, right? You know, if you're working with this basis, and then you look at v1 plus v2, it's essentially so if the length of v1 and the length of v2 are larger than 1, this is a vector which overall length is smaller than the length of either of its components. Annoying, yes. That's why we like to work with orthonormal bases, because it doesn't happen for orthonormal bases. Generally speaking, I don't like to work on analysis with bases like this. Theorems that are known for analysis of finite dimensional vector spaces hold for bases like that. But you don't want to prove anything in a basis like that. I mean, anyway. This is one of those things I try to talk about in advance, but probably regret talking about because it doesn't really... Anyway, I'll shut up. What's that? Hilbert space good, Banach space bad. Yeah, well, I mean, you can work in a... You can look at a stupid basis in a Hilbert space. I mean, yeah, Hilbert space supports orthonormal bases, right? But that doesn't mean that once you're given a basis, it's necessarily orthonormal. And the theory for non-orthonormal bases is uglier. Shivers. Oh, okay, so that's less than that, that's less than that. And, of course, you know, triangle inequality looks like that because the norm of the length of I is 1, so it kind of, that happens. And anyway, in short, though, definition, getting to the point finally, the integral of f of x dx is equal to the integral of u of x dx plus I times the integral of v of x dx. Or as we'll probably write it, the integral of f is the integral of u plus I times the integral of v in our typically unadorned integration. Yeah. He says, finally, if E is a measurable subset of Rd and f is a complex valued measurable function on E, then we say f is Lebesgue integrable on E if f chi E is integrable on E, in which case we define the integral over E of f is equal to the integral over f chi E. So that's still the deal. And he says the collection of all complex valued integrable functions on a measurable subset E of D forms a vector space over C. Indeed, if f and g are integrable, then so is f plus g, and we get triangle inequality. And the monotonicity of the integral yields, he's just arguing that the integral of the sum of two integrable functions is again integrable. And he says that the integral continues to be linear over the complex numbers as well. So, all right. So that brings us to the next thing I'm excited to talk about, which is section 2 here. I almost forgot about this. My bad. Which is the space of L1 integrable functions. So he talks about the properties of L1 integrable functions for a couple pages here. And then he talks about invariance properties. That leads to a proof that the convolution of two functions is measurable. And then he's got about 10 pages on Fubini past that. What time is it? All right. So I think there's a pretty good chance I can explain the L1 stuff in the 10 minutes we have left. There's not really anything to prove here much. It's just things I want to tell you. All right. So the space of L1 integrable functions. All right, so for any integrable function f on Rd, we define the norm of f as follows. Norm of f equals norm of f, excuse me, in the L1 sense, which equals the norm of this litany of redundant notation will be over here eventually. The norm of L1 of Rd equals to, you just integrate the absolute value of f of x dx over Rd. Again, the preamble to this equation is suppose f is integrable, right? So we're assuming that that integration is, well defined and finite. He says the collection of all integrable functions with the above norm gives a somewhat imprecise definition to the space L1 Rd. So all such f Rd to R form L1 Rd. Well, not really. Right. All right, so what do you need for a norm? what's one of the important, what does it take to be a norm? Let's review. What properties do we need for a norm? I'll start us out with the easy one. Norm of f plus g less than or equal to norm f plus norm g. I just got done explaining that that's true even if we extend to complex valued functions. We could still write that. That's the easy, I think that's the easy one. Not the easy one to prove, but it's true. The norm of 0 is 0. That's true. But a greedier way of saying this, a greedier way of saying what we want is the norm of f is equal to 0 if and only if f is equal to the 0 vector. And that's actually the one that gets us into trouble. Because the integral of f's value of f of x dx over rd equals to 0 only implies what? I mean, one direction of this arrow is hunky-dory. This one, check. The 0 function definitely integrates to 0, but the other direction is just not true. We don't get that f of 0. We get f of x equals to 0 almost every x. Almost every x is not all x. So in fact, the set of all functions with this quote-unquote norm is not a norm in space because we don't have the necessary, I mean, that's not the right property. We should only have 0 having norm 0. What's the resolution of this? Take quotient is one way to look at it. Very good. So basically L1 of RD is actually, it's like f such that the integral of f, RD is less than infinity, and what does f mean? G such that f is equal to g almost everywhere, right? So what I'm trying to say is you look at equivalence classes of functions where they're equal almost everywhere. So the two functions are thought of as equal if they are the same everywhere except on a set of measure 0. So that resolves the problem. I mean, this is equivalent to the 0 function in the sense of equivalent, because it's only differing from the 0 function on a set of measure 0. And so not for functions, but for equivalence classes of functions, that defines a norm. And the space of all such equivalence classes is known as L1RD. But it's such a sort of innocuous kind of equivalence that we might just say functions and forget sometimes that we're really talking about equivalence classes of functions if we're not careful.
Is this similar to the taxi cab space?
No, but I don't know about taxi cab, but I think it's very similar to differential equations where we take the inverse Laplace transform and pretend it's just one thing.
I'm trying to remember what the Laplace transform is.
It does equal to, it is kind of equivalent to the taxi cab if you
Oh.
consider on a discrete.
It's equivalent to taxi cab if I consider on discrete set.
Oh, yeah, because like that's been called common measure and you just count
Oh, oh, okay. Yeah, I'm not sure what you guys are talking about at the moment, but that doesn't mean it's not worth talking about. It means I'm not.
You can consider L1 over any measurable space also.
Oh. Oh, okay. Yes.
And there is a measurable space that you just count.
That is true. At the end of this section, he mentions that everything we're doing right now, it can be done or you can replace RD with a measurable set and say the same things. okay, let me move along here. So with that in mind, keeping in mind that we're working with equivalence classes rather than just functions, look at this. Right after the paragraph, he gets done talking about that we're going to work with equivalence classes. What's he say? Suppose f and g are, and I quote, two functions. And see, no one can bear it. no one can bear saying two equivalence classes of functions, and that's fine. All right. Anyway, number one, the norm of look at this is such the notation. I mean, I understand. I know fine. You want to make nuanced comments about different choices of notation and so forth, then this is what it costs you. But I'll tell you what, if you're doing a specific problem in some kind of calculation, you drop this mighty fast to triangle inequality. Good thing is this is good as at the end of my lecture because I don't. This is wearing me out. I see. He really does mean functions. I see what he's doing. But they're not functions in L1RD. If you say, whatever, I'm going to stop. I don't know, given all the notation he's got here, why doesn't he invent a notation for the functions versus the equivalence classes, you know? He's gotten this far. Why not invent yet another symbol? Like, that one could be functions, and L1 mod squiggle could be the actual L1. You know? I don't know. Whatever. L1 has to be a norm space, yeah. It is convention to call that actually L1, that's true. Metric on L1. All right, finally. So these are properties of this L1RD. And I'll just tell you. Again, this is on the equivalence classes. I mean, he's saying functions, but he doesn't mean it. He really means the equivalence classes. This defines a metric on the equivalence classes of functions. Like I said, I mean, he can't make up. They're not making up. They're refusing to adopt one viewpoint. In their defense, it's a confusion that we have had with us in calculus from the very beginning. We talk about the indefinite integral when what we really mean is the equivalence class of functions which differ by a constant. Just rather than writing curly bracket f of x plus c such that c is a real constant, we write f of x plus c, no curly bracket. Yeah, I think we're getting. So what he then goes on to say is that with respect to this metric, it's said to be complete if Cauchy sequences necessarily converge, right? And he says our main goal of completing the space of Riemann integrable functions will be attained once we have established the next important theorem of Rietz-Fischer, I guess. The vector space L1 is complete in its metric. So this, in fact, is complete. But we replaced functions with equivalence classes of functions, truth be told. And then corollary 2.3, I think, is actually the explicit completeness. It says, if you have a sequence of functions which converges to f in L1, then there exists a subsequence, fnk, such that fnk converges to f of x for almost every x. And that would mean that it converges to an L1 function, since its convergence is almost everywhere. And then he mentions that the following families of functions are dense in L1RD: simple functions, step functions, and continuous functions of compact support. The reason this is important is that if you have a family of something that are dense in something else, if you can prove that a particular property is true for a dense subset, then often we can pass to the limit. I mean, the fact that they're dense means that the limit of those things gets you everything. And so proving it for a dense subset proves it for everything, which is, like one of the major ideas in modern analysis techniques. And then he talks about invariance properties, but I guess I'll start there next time. I mean, we don't have to do everything today. So my goal next time is to sort of more or less pick up where we are right here. And I'm hoping to say a word or two about the Fourier inversion formula and try to tie that together with at least a few comments about Hilbert spaces. Basically, I'm going to say nothing about Chapter 3. Chapter 3 is essentially the fundamental theorem of calculus for measure theory. It talks about how differentiation and integrations continue to be inverse processes in the context of measure theory, which is interesting, but not nearly as interesting as the Hilbert space chapter, which I'd like to at least give you guys some sort of big picture parting thoughts for. Because you'll probably go to grad school and take a course in them, and it would be nice to have some kind of fuzzy notion of what a Hilbert space is before we're done. I think that's worth our time, more than me fussing through the details of why the fundamental theorem of calculus is still true in this context. Yeah.